What if the universe is twice as old as we think today? This hypothesis may seem to go against standards, but there is evidence that makes us ponder. So how do we know the age of the universe? These are very difficult calculations, not only for the universe, but for estimating the age of anything. To know the age of a tree, you can count the rings in its trunk. The problem is you need a cross-section, and you only know the exact age of the tree after it has been filled. To estimate the age of ancient fossils, you can analyze its radioactive isotopes. The issue here is that laboratory capabilities must be sufficient. Regarding the universe, scientists cannot simulate massive spatial structures in a lab to study them. Instead, they turn the universe itself into a gigantic laboratory. However, this requires very sophisticated and modern technological foundations. Recent discoveries by the James Webb Space Telescope of rapidly evolving galaxies just 325 million years after the Big Bang have led some cosmologists to propose an entirely new theory. The universe might be much older than we think, possibly twice the current estimate of 13.8 billion years. Before delving deeper into this matter, let's discuss the figure of 13.8 billion years. How did scientists calculate the age of the universe? Here are the two main methods. The first method involves finding the oldest stars by calculating their age, because the universe cannot be younger than the stars. The drawback of this method is the high margin of error and the varying lifespans of different stars. More importantly, it's extremely difficult to determine which star is the oldest in the universe and whether that star still exists or has exploded long ago. Instead of pursuing an impossible search, scientists turn their research to star clusters. To calculate the age of a star cluster, we need to understand the life cycle of a star, the physical logic in the main sequence diagram, and definitely observations from telescopes. For a star, its lifespan is directly related to its mass. The larger and heavier the star, the shorter its lifespan, typically around 1 million years for type O stars. Conversely, tiny stars of type M can live up to 50 billion years, or even hundreds of billions of years. So how do we calculate the age of a star cluster? Generally, a star cluster will contain hundreds of thousands to millions of stars, most of which form during the same period. When observing any star cluster, we assume that the stars within that cluster are at the same distance from Earth. This distance affects the light intensity and, therefore, the measurements. If we assume all stars in the cluster are at the same distance, the light intensity can be slightly adjusted, but the calculations will be much simpler and the age estimation error extremely low, around 0.0058%. After measuring the distance, the next step is to collect data on color, brightness, or overall temperature of the entire cluster. Finally, this data is matched with the main sequence diagram. The main sequence diagram is a type of chart that allows classification and tracking of star evolution. For example, a blue star of type O has an extremely high temperature and intense brightness, with its lifespan in the main sequence only measurable in millions of years. After burning all its fuel, it evolves into a red giant star. At this stage, the star changes completely in color and size, turning a bright red, expanding significantly, and its surface temperature drops. If the star cluster contains many red giant stars, it indicates that the large stars in the cluster have mostly evolved and their main sequences have ended. If we categorize by star type, we get the age of each type as follows. Type O stars are blue, with a lifespan of no more than 10 million years. Type B stars are blue-white, with a lifespan of no more than 100 million years. Type A stars are white, with a lifespan of no more than 1 billion years. Type F stars are yellow-white, with a lifespan of no more than 5 billion years. Type G stars are yellow, with a lifespan of no more than 10 billion years. Our Sun is a Type G star. Type K stars are orange, with a lifespan of no more than 50 billion years. Type M stars are red, with a lifespan of up to 100 billion years. Observations show that the oldest star clusters only contain small stars, lighter than the Sun by about 30%. Moreover, there are no larger stars present. This suggests that the cluster's age ranges between 11 and 18 billion years. Thus, once we know the lifespans and evolution of each star type, scientists can use this information to calculate the age of the star cluster. For example, the star cluster NGC 6397 contains more than 400,000 stars. By measuring the brightness and temperature of each star, we can match them to the main sequence diagram. Scientists have estimated the cluster's age to be around 13.4 billion years. This is the first method that helps estimate the age of the universe, and as its name suggests, although very meticulous and complex, it only allows for estimations. If a precise number is desired, another method must be used, the method of time extrapolation. This method is quite simple. We only need to calculate the universe's expansion constant and then measure the redshift rate of the cosmic microwave background radiation to determine the universe's age. The universe's expansion constant is its rate of expansion over time and distance. This constant was first calculated by Edwin Hubble in the 1920s, but due to observational technology limitations, the error margin was quite large. Today, the most accurate measurements with the least errors are made by the Planck Space Telescope of the European Space Agency. The expansion constant measured is 67.4 km per second per 3.26 million light years. With such an expansion rate, the cosmic microwave background has a redshift factor of about 1/1100, corresponding to a universe age of 13.82 billion years. It should be noted that the cosmic microwave background is believed to be the oldest layer of photons ever to appear in the universe, existing even before the first atoms and shortly after the universe's birth, about 300 million years. Given all this information, we understand why scientists calculate the universe's age this way. Although it may not be 100% accurate, it is entirely based on solid calculations that we can trust. However, if these calculations and measurements are so conclusive, why do some still believe the universe is much older? This hypothesis stems from the latest observations by the James Webb Space Telescope. It has captured very distant and very ancient galaxies that do not resemble the primitive galaxies we thought. They are enormous, containing many stars, and are incredibly massive. Until now, our understanding of the universe suggests that galaxies need time to grow by accumulating stars and building structures through various processes. Logically, ancient galaxies did not have enough time to grow so large. Could it be that we do not fully understand how galaxies form, or is the universe much older and more extensive than we know? The James Webb is indeed a powerful machine, capable of firmly strengthening our existing knowledge or possibly breaking the limits we have not yet imagined. However, we must proceed with caution, for if we want to replace old knowledge with new knowledge, science must find extraordinary evidence that can change our entire worldview and understanding of the universe.